Rates of change and behavior of graphs. Gasoline costs have experienced some wild fluctuations over the last several decades. Table 1 lists the average cost in dollars of a gallon of gasoline for the years 2005 through 2012. The cost of gasoline can be considered as a function of year. If we were interested only in how the gasoline prices changed between 2005 and 2012, we can compute that the cost per gallon had increased from $2.31 to $3.68, an increase of $1.37. While this is interesting, it might be more useful to look at how much the price changed per year. In this section, we will investigate changes such as these. Finding the average rate of change of a function. The price change per year is a rate of change because it describes how an output quantity changes relative to the change in the input quantity. We can see that the price of gasoline in Table 1 did not change by the same amount each year, so the rate of change was not constant. If we used only the beginning and ending data, we would be finding the average rate of change over the specified period of time. To find the average rate of change, we divide the change in the output value by the change in the input value. Average rate of change equals the change in output over the change in input equals delta y over delta x equals y2 minus y1 over x2 minus x1 equals f of x2 minus f of x1 over x2 minus x1. The Greek letter delta signifies the change in a quantity. We read the ratio as delta y over delta x, or the change in y divided by the change in x. Occasionally, we write delta f instead of delta y, which still represents the change in the function's output value, resulting from a change to its input value. It does not mean we are changing the function into some other function. In our example, the gasoline price increased by $1.37 from 2005 to 2012, and over 7 years, the average rate of change was delta y over delta x equals $1.37 over 7 years, which is approximately $0.196 per year. On average, the price of gas increased by about 19.6 cents each year. And other examples of rates of change include a population of rats increasing by 40 rats per week, a car traveling 68 miles per hour, distance traveled changes by 68 miles each hour as time passes, a car driving 27 miles per gallon, distance traveled changes by 27 miles for each gallon, the current through an electrical circuit increasing by 0.125 amperes for every volt of increased voltage, and the amount of money in a college account decreasing by $4,000 per quarter. Rate of change. A rate of change describes how an output quantity changes relative to the change in the input quantity. The units on a rate of change are output units per input units. The average rate of change between the two input values is the total change of the function values. Output values divided by the change in the input values. Delta y over delta x equals f of x2 minus f of x1 over x2 minus x1. How to? Given the value of a function at different points, calculate the average rate of change of a function for the interval between two values, x1 and x2. 1. Calculate the difference. y2 minus y1 equals delta y. 2. Calculate the difference. x2 minus x1 equals delta x. And 3. Find the ratio of delta y over delta x. Using a graph to determine where a function is increasing, decreasing, or constant. As part of exploring how functions change, we can identify intervals over which the function is changing in specific ways. We say that a function is increasing on an interval if the function values increase as the input values increase within that interval. Similarly, a function is decreasing on an interval if the function values decrease as the input values increase over that interval. The average rate of change of an increasing function is positive, and the average rate of change of a decreasing function is negative. Figure 3 shows examples of increasing and decreasing intervals on a function. While some functions are increasing or decreasing over their entire domain, many others are not. a value of the input where a function changes from increasing to decreasing as we go from left to right, that is, at the input variable increases, it is called a local maximum. If a function has more than one, we say it has a local maxima. Similarly, a value of the input where a function changes from decreasing to increasing as the input variable increases is called a local minimum. The plural form is local minima. Together, local maxima and minima are called local extrema, or local extreme values of the function. The singular form is extremum. Often, the term local is replaced by the term relative. In this text, we will use the term local. Clearly, a function is neither increasing nor decreasing on an interval where it is constant. A function is also neither increasing nor decreasing at extrema. And note that we have to speak of local extrema because any given local extremum, as defined here, is not necessarily the highest maximum or lowest minimum in the function's entire domain. For the function whose graph is shown in figure 4, the local maximum is 16 and it occurs at x equals -2. The local minimum is -16 and it occurs at x equals 2. To locate the local maxima and minimum from a graph, we need to observe the graph to determine where the graph attains its highest and lowest points, respectively within an open interval. Like the summit of a roller coaster, the graph of a function is higher at a local maximum than at a nearby points on both sides. The graph will also be lower at a local minimum than at neighboring points. Figure 5 illustrates these ideas for a local maximum. These observations lead us to a formal definition of local extrema. Local minimum and local maxima. A function f is an increasing function on an open interval if f of b is greater than f of a for any two input values a and b in the given interval where b is greater than a. A function f is a decreasing function on an open interval if f of b is less than f of a for any two input values a and b in the given interval where b is greater than a. A function f has a local maximum at x equals b if there exists an interval AC with a less than b and b less than c such that for any x in the interval AC, f of x is less than or equal to f of b. Likewise, f has a local minimum at x equals b if there exists an interval AC with a less than b and b less than c such that for any x in the interval AC, f of x is greater than or equal to f of b. Analyzing the toolkit functions for increasing or decreasing intervals. We will now return to our toolkit functions and discuss their graphical behavior in Figure 10, Figure 11, and Figure 12. Constant function, f of x equals c, increasing or decreasing. It's neither increasing nor decreasing. Identity function, f of x equals x, increasing or decreasing. It is increasing. Quadratic function, f of x equals x squared, increasing on 0 to infinity, decreasing on negative infinity to 0, minimum at x equals 0. Cubic function, f of x equals x squared, is increasing. Reciprocal function, f of x equals 1 over x, decreasing on negative infinity to 0 union 0 to infinity. Reciprocal squared, f of x equals 1 over x squared, increasing on negative infinity to 0, decreasing on 0 to infinity. Cube root, f of x equals the cube root of x, increasing. Square root, f of x equals the square root of x, increasing on 0 to infinity. Absolute value, f of x equals the absolute value of x, increasing on 0 to infinity, and decreasing on negative infinity to 0. Use a graph to locate the absolute maximum and absolute minimum. There is a difference between locating the highest and lowest points on a graph in a region around an open interval locally and locating the highest and lowest points on the graph for the entire domain. The y-coordinates output at the highest and lowest points are called the absolute maximum and absolute minimum, respectively. To locate absolute maxima and minima from a graph, we need to observe the graph to determine where the graph attains its highest and lowest points on the domain of the function. Not every function has an absolute maximum or minimum value. The toolkit function f of x equals x cubed is one such function. Absolute maxima and minima. The absolute maximum of f at x equals c is f of c, where f of c is greater than or equal to f of x for all x in the domain of f. The absolute minimum of f at x equals d is f of d, where f of d is less than or equal to f of x for all x in the domain of f. Access this online resource for additional instruction and practice with rates of change. Average rate of change, openstackscollege.org. Composition of functions. Suppose we want to calculate how much it costs to heat a house on a particular day of the year. The cost to heat a house will depend on the average daily temperature, and in turn, the average daily temperature depends on the particular day of the year. Notice how we have just defined two relationships. The cost depends on the temperature, and the temperature depends on the day. Using descriptive variables, we can notate these two functions. The function c of t gives the cost c of heating a house for a given average daily temperature in t degrees Celsius. And the function t of d gives the average daily temperature on the day d of the year. For any given day, cost equals c of t of d, means that the cost depends on the temperature, which in turn depends on the day of the year. Thus, we can evaluate the cost function at the temperature T of D. For example, we could evaluate T of 5 to determine the average daily temperature on the 5th day of the year. Then we could evaluate the cost function at that temperature. We would write C of T of 5. By combining these two relationships into one function, we have performed function composition, which is the focus of this section. Combining functions using algebraic operations. Function composition is only one way to combine existing functions. Another way is to carry out the usual algebraic operations on functions, such as addition, subtraction, multiplication, and division. We do this by performing the operations with the function outputs and defining the result as the output of our new function. Suppose we need to add two columns of numbers that represent a husband and wife's separate annual incomes over a period of years. With the result being their total household income, we want to do this for every year, adding only that year's income, and then collecting all the data in a new column. If W of Y is the wife's income and H of Y is the husband's income in year Y, and we want T to represent the total income, then we can define a new function. T of Y equals H of Y plus W of Y. If this holds true for every year, then we can focus on the relation between the functions without reference to a year and write T equals H plus W. Just as for this sum of two functions, we can define difference, product, and ratio functions for any pair of functions that have the same kinds of inputs, not necessarily numbers, and also the same kinds of outputs, which do have to be numbers so that the usual operations of algebra can apply to them, and which also must have the same units or no units when we add and subtract. In this way, we can think of adding, subtracting, multiplying, and dividing functions. For two functions, f of x and g of x with real number outputs, we define new functions f plus g, f minus g, fg, and f over g by the relations f plus g of x equals f of x plus g of x, f minus g of x equals f of x minus g of x, fg of x equals f of x, g of x, f over g of x equals f of x over g of x, where g of x does not equal 0. Create a function by composition of functions. Performing algebraic operations on functions combines them into a new function, but we can also create functions by composing functions. And when we wanted to compute a heating cost from a day of the year, we created a new function that takes a day as input and yields a cost as output. The process of combining functions so that the output of one function becomes the input of another is known as a composition of functions. The resulting function is known as a composite function, and we represent this combination by the following notation. F of g of x equals f of g of x. We read the left-hand side as f composed with g at x, and the right-hand side as f of g of x. The two sides of the equation have the same mathematical meaning and are equal. The open circle symbol is called the composition operator, and we use this operator mainly when we wish to emphasize the relationship between the functions themselves without referring to any particular input value. Composition is a binary operation that takes two functions and forms a new function, much as addition and multiplication takes two numbers and gives a new number. However, it is important not to confuse function composition with multiplication because, as we learned above, in most cases, f of g of x does not equal f of x g of x. It is also important to understand the order of operations in evaluating a composite function. We followed the usual convention with parentheses by starting with the innermost parentheses first and then working to the outside. In the equation above, the function g takes the input x first and yields an output g of x. Then the function f takes g of x as an input and yields an output f of g of x. In general, f composed of g and g composed of f are different functions. In other words, in many cases, f of g of x does not equal g of f of x for all x, and we will also see that sometimes two functions can be composed only in one specific order. For example, if f of x equals x squared and g of x equals x plus 2, then f of g of x equals f of x plus 2 equals x plus 2 squared equals x squared plus 4x plus 4, but g of f of x equals g of x squared equals x squared plus 2. These expressions are not equal for all values of x, so the two functions are not equal. It is irrelevant that the expressions happen to be equal for the single input value x equals negative half. Note that the range of the inside function, the first function to be evaluated, needs to be within the domain of the outside function. Less formally, the composition has to make sense in terms of inputs and outputs. Composition of functions. When the output of one function is used as the input of another, we call the entire operation a composition of functions. For any input x and functions f and g, this action defines a composite function, which we write as f of g, f composed of g, such that f composed of g of x equals f of g of x. The domain of the composite function, f composed of g, is all x, such that x is in the domain of g, and g of x is in the domain of f. It is important to realize that the product of functions fg is not the same as the function composition f of g of x, because in general, f of x, g of x does not equal f of g of x. Q&A. Are there any situations where f of g of y and g of f of x would both be meaningful or useful expressions? Yes, for many pure mathematical functions, both compositions make sense even though they usually produce different new functions. In real-world problems, functions whose inputs and outputs have the same units also may give compositions that are meaningful in either order. Evaluating composite functions. Once we compose a new function from two existing functions, we need to be able to evaluate it for any input in its domain. We will do this with specific numerical inputs for functions expressed as tables, graphs, and formulas, and with variables as inputs to functions expressed as formulas. In each case, we evaluate the inner function using the starting input and then use the inner function's output as the input for the outer function. Evaluating composite functions using tables. When working with functions given tables, we read input and output values from the table entries and always work from the inside to the outside. We evaluate the inside function first and then use the output of the inside function as the input to the output function.